we've got Chelsea and Shinichi Mochizuki. One of the questions that came in earlier, which I thought I'd defer to this panel session, is the impact of AI and its ability to help with some of this auto-formalization, but also exploration on things like recruitment into graduate schools. Is that likely do you have any feeling for whether it's going to put people off, it's going to attract people? You spoke, Chelsea, about sort of the demands of what a modern software engineer and proof engineer is going to need in this AI age. So perhaps I'll throw the question to you first.
Yeah, I mean, it's a good question. And as someone who is pretty recent out of grad school myself, it's kind of interesting to think about where I would have been at if I was looking at doing a formalization PhD like when I was making that decision now. I think in some ways there was always, and this is from a formalization perspective, there was always this kind of interest in, well, if you're going to do a PhD in this, it can't just be formalize it. You have to do something kind of a bit more interesting with it. And I think in that respect, if we look at the proof engineering side of it and not just, okay, as long as the community is accepting, well, just auto-formalizing isn't the only way forward, but there's all this other interesting stuff around it that we can do in partnership. I think that shouldn't be a detractor. I think it's just a different way of doing something. But I think it's definitely going to require that recognition of all the other aspects of it, rather than just getting the verification component done. Because if that's all we're concerned about, we're in a different place now for that. So yeah, I personally think there's a lot of still very exciting problems to explore around it, and I think it's an interesting kind of time for doing it. And in that respect, I think there's a lot of potential for new students and people just coming through. But I do completely recognize that it also makes things sometimes maybe a little bit scary. It's both exciting and scary in many different ways when you see kind of how far things have come so quickly and keeping up with that.
Thank you. Shinichi, do you have anything to add?
Yeah. So, of course, I'm not an expert on formalization. I'm looking at it from the point of view of mathematics. Recently, I have been strongly encouraging my graduate students to study Lean, and also to so, in fact, one of my graduate students is already an expert on Lean, and in fact, he's very much involved with Archon. And so, in other words, so he's from China, and he has strong contacts with this research group in Beijing University, and so he's very much involved with auto formalization on the one hand, and NWN geometry, and he's also interested in IUT on the other. And so, from my point of view, this is something that increasingly, so we get a certain number of graduate students from China, a sort of steady flow of graduate students from China. And this has been one thing that has been remarkable from my point of view, is just the very deep sort of connections between Chinese math graduate students and auto formalization or formalization in general. They're all very much into, well, not all of them, but many of them are very much into this already. And I'm trying to encourage the Japanese graduate students and also the Chinese graduate students who are not already involved with it to get more involved. And so, from my point of view, auto formalization is, I don't see the scariness of it. I guess maybe I'm just not sufficiently knowledgeable about it to realize the scariness of it. But it seems just like sort of something that's very exciting and interesting. And so I've heard all these stories about the bloated nature, the redundant nature of auto-formalized code. And so it seems to me that it's it's just one step in a long assembly line. And so I don't see the scariness of it, because I think it's just sort of the one step, or the first step, or sort of one rough approximation to what mathematicians are ultimately aiming for. And so anyway, that's my point of view, I guess.
Yeah, thank you very much. I think probably we're in this interesting phase, right, where it is an exciting area of development. We're still learning how to use these things and how to teach graduate students, if not undergraduates, how to use proof verification. I'm reminded of when I was a PhD student, a colleague in biochemistry was doing a PhD thesis and had to pivot because the structure that they were working on was published. And we could very much be in that situation where someone who perhaps isn't using proof verifiers but he's researching in a sort of more traditional mathematical way, might have to pivot because something becomes formalized that they were working on. So it's an interesting period anyway. Yang-Hui, you're back with us, which is great.
Yeah, sorry, I'm just drifting in and out of Wi-Fi. I think my Wi-Fi isn't very stable. Sorry about that. It's been a technical hurdle one another today. Sorry about that.
No problem at all. Another question we've got for the panel. Do you think that mathematical society at large is going to lose sight of the other aspects of formalization that are going to focus on just get the proof verified? And this was something that you sort of all touched on in various different ways. What is the purpose of understanding and proof? That certainly seems to be the headlines, right?
Yeah, I think for me this is one of the, as I think, like a potential risk, and I hope if we can really highlight as a community kind of the benefits of not just focusing on it's verified, that we can kind of not completely go down that path. I think, again, if we can appeal to that kind of maybe more philosophical, and again, I'm coming from this with not being a full mathematician, right? So I'm coming from this from a slightly outsider perspective. But if we can come up with this more philosophical kind of way of why have we always proven math, and think of it from that perspective, and then highlight formalization as just being another way of approaching that and getting those insights, we can hopefully avoid that problem of it just becoming about getting it verified.
Yes, thank you. And I'm struck that, of course, this was very much the purpose, Shinichi, of what you're trying to do, the communication aspect.
Right. The communication. It strikes me,
even linking with the Yang-Hui stuff, that there is an essence here where the community is asking both for almost proof by authority. If Lean or Isabel says it's true, then I'll believe it. But he's also looking for that refactoring that's required in order to communicate and perhaps rethink the structure of a proof in order to understand it at a deeper level.
Yeah, I often get asked the question, if at some time in the distant future where some, axiom math or coupled with Lean produces a 10 billion line proof of the Riemann hypothesis, which is verified, what do we do as a community, and how do we appreciate that? I mean, how do we distill that into something that is, even if it's written out 10 billions of lines, imagine, 10 billion lines of Lean turns into 20 billion lines of LaTeX. How do we read this, and how do we communicate and appreciate that it's a beautiful proof of the Riemann hypothesis? And I think that's I don't have a good answer to that question.
So this is basically a repetition of what I said earlier. I think it's just the first step in a long assembly line. I don't think there's anything sort of problematic about it. I think that once the code is written, even if it's very verbose and bloated and so on, the code can be fed back into AI and analyzed, and it's just going to be sort of this I don't want to call it an endless loop, but we can keep sort of decomposing it and feeding it back into to AI and all sorts of other things. And it's just the starting point of a story. It's not verification is not the end of the story. It's the starting point. And then if it creates data that is interesting to analyze, and then we have to start analyzing it and decomposing it and feeding it back into AI and just so anyway, it's just the beginning of the story. It's not the end.
No, absolutely. And at least in part, this is an issue that the mathematical community has wrestled with forever, right? That there are some proofs that really amount to thousands of pages or concepts that only one or two individuals really grasp thoroughly. And as a community, how do we decide whether we really understand that and what's sufficient? It's just moved who or what understands it. Again, what does understanding mean to a machine, right?
Yeah.
I'm an optimist. I think it's kind of like, I think it'll bring mathematicians together so that we can appreciate it together and analyze it together. And then there's something more, and that humanity, I think, it's not going to be replaced by any form of AI, and no matter how fast AI is going to develop, it's like live theater. It's never going to be replaced, no matter what happens.
Yeah, and I think that's actually almost really emphasized by what we've seen since formalization has become something that the mathematical community is starting to embrace. It has turned from being something where you've required access to sick individuals and that kind of thing, and now just how quickly technology has grown, this community that you start to see online, it's really quite extraordinary. And I think that's enabled a lot that just wouldn't have happened before.
Think getting back to the original question and also this this comment by Professor He, that so I think it has the potential to bring people together and to be used effectively in this way. But it also has the potential, like any technology, of being abused or used for going in the opposite direction. And so I think that's sort of what the question is about. I think it has to be a conscious effort to say, well, we envision it as something that brings us together and that is constructive and creates sort of new opportunities and it creates more wealth. It doesn't sort of just consume wealth and it's not a destructive thing, but it's a constructive thing that brings us. I think we have to have this shared understanding that this is what we're going to do, this conscious understanding that this is the direction in which we're going to take things.
I think you're right. I think we have to, if this is what we want, I'm sure we do, we have to consciously build that and curate that community working together, not least because the pace of development can be so fast that groups could very easily fracture, splinter, with results not being able to be almost published fast enough for the community to keep up. So both are things are in tension, and it's going to require the community to curate that and make it happen. There's another question related to something I asked yesterday, actually, which is in teaching, most mathematical proofs are presented forward style, while systems such as Lean and Isabel also allow for a more explorative backward style process. Has this changed how you, if you've interacted with these systems, approach proof yourself? And how might it change the way we sort of teach and work on proofs?
It's a really good question. You go first. I'm still thinking.
No. I was just going to talk because no one else was talking. But so please go ahead.
It's interesting for me because I have been using proof assistance since I was an undergraduate, and so I have been thinking this way for quite a while. And so it's almost sometimes challenging to go back and to think of what happens if I'm not necessarily thinking that way, which I think is something quite interesting, because obviously we're going to get more and more undergraduates now, particularly in maths as well, who are, learning proof alongside learning these systems. And that might be quite interesting to see what happens in 5 or 10 years' time, as to how that impacts how people are approaching mathematics. I would say I still do a lot of forward-style reasoning, and particularly Isabel, the Isar language actually quite encourages that. But similarly, I guess just coming more from a computer science perspective, it's very common to actually more reason backwards in that perspective, and to break a problem down. And so I think they work quite well together. But yeah, it could be quite interesting to see how that affects teaching moving forward, generally.
I agree. I mean, it's something that I've sort of puzzled over, and
Yeah.
I only in recent years, having played with Lean and previously Mizar, that I realised how entrained forward reasoning is as a behaviour. And I think our students more naturally sort of oscillate between the two, with very little evidence other than my observations of what they try to do in writing down proofs of theorems. They seem to want to be working at both ends, which, as long as one is careful, of course, is a very sensible thing to do.
Okay, so can I say something?
Yeah, please do.
So with regard to the forward reasoning or versus backward reasoning, I think that at least in my experience with regard to formalizing IUT, we got to the point. I think there were sort of arguments about how to proceed. Should one go just sort of start from the first paper and go linearly, or start from the back, from the final portion of the proof? And I think that because the technology is such that just going in a straightforward linear fashion would be so overwhelming in terms of the time and effort that's required. Ultimately, everyone involved that I have talked to has ended up sort of giving up on this and concentrating on starting from the final portion, which has received the most public attention. And so, but on the other hand, when doing that, I think that in terms of looking at the whole theory, in some sense, it's natural when approaching formalizations to start from the final portion. But within the final portion, there's still, I think, the sort of the natural direction of going in the forward direction for formalizing that final portion. So locally, it's sort of locally going forward, but globally going backwards. And as I pointed out in my talk, I found the sort of the tiny portion of formalization that has already been done to be very refreshing, in that it stimulated sort of a reorganization of the argument. And so I think that from the point of view of students, so I think this is something that is related to what Paola Iannone talked about yesterday. It's I think it influences students who learn formalization sort of simultaneously with mathematics, does have an overall positive influence in the way they write proofs, because so there was this issue about that it seems to discourage people from thinking about examples. I don't know how essential this aspect is. So she gave this data that it seems to discourage students from thinking about examples. But I think that the overall effect is that by learning formalization simultaneously with mathematics, you sort of don't, from the student's point of view, you no longer see the point of sort of starting to formulate a bogus argument, because you already sort of, unless you're, I guess you have to be a certain level of student, but you sort of think about things from the point of view of, okay, how am I going to formalize this? And you start thinking about writing a proof, even when you're not formalizing, in a way that sort of preemptively overcomes the issues that you have to think about when you have to when you confront the issue of formalizing. And so this is, I found that I had this, that I already experienced this when I was thinking about how to reorganize the arguments for the final portion of IUT. And I think this can be this can have a positive effect for students. And so that's why, as I said previously, I've been encouraging my graduate students to study, to learn about lean formalization.
Absolutely. And I think partly this is because for those students, when we think back to Paolo's talk, it's because of the way that the community uses Lean, and Lean was developed in order to create these proofs and formal verifications of proofs. But it can be used for examples and verifying certain things, for examples and counterexamples. We just haven't perhaps caught up yet with the sorts of resources we need and the ways of teaching it, and that mesh with what our undergraduates want. And maybe other proof assistants like Isabel, which focus sometimes more on the algorithmic aspects and having some computations that are output at the end, have already got there in some sense before the Lean community has. I think this links in also with Yang-Hui's stuff on sort of this exploratory discovery using data, because we're now in a position where you take Python, Mathematica, whatever computer algebra software you want, and you can generate hundreds of thousands of instances of objects that even students can explore and extract invariants and all sorts of things with. And so that can also motivate, alongside the formal proof verification, the study of mathematics. I don't know if you want to say more, Yang-Hui.
Yeah, no, absolutely, because it's kind of, every student almost everywhere has all of the internet available and a supercomputer in his or her own hands at any time to do experiment. And I think this is it's amazing. This is unthinkable. I always say, I think about, imagine what Gauss could have done if he had this sort of stuff. Back in the day when Gauss was thinking of the prime number theorem, he had to calculate primes in the 100,000 range by hand, and that was that amount of time being saved would create kind of, we're parallel processing the minds of Gauss right now, so which is kind of really, really reassuring. And this is just on data mining, and before you can feed all of this, any statements of conjectures and discoveries into formalization. So it's a nice pipeline to efficiently explore mathematics.
Absolutely. There's a question, I think that's primarily for Shinichi, but it's about collaboration more generally. So it is, what's your view of the LANA project from the Zen Mathematics Center? Will you and your colleagues collaborate with them? Are you aware of their progress?
So it's a complicated relationship because there's a certain overlap of members. There's a non-trivial intersection of a non-empty intersection of my research group and the LANA group, and also people who were previously at RIMS who have moved to the ZMC. So it's a complicated relationship because my approach to doing things is often somewhat different from Fumiharu Kato's approach. So Fumiharu Kato is the head of the LANA project. So we're in close communication, but and there's substantial interaction, but it doesn't always go so smoothly. So that's that. So I continue to have high hopes in the long run for what this Lana project can do, but on the other hand, I've been substantially disappointed by what they've been doing sort of without my involvement. And so I think that they've sort of shifted. So the Lana project started in 2024, and I only really got involved with formalization in 2025. So I think they've shifted now to previously they were sort of strongly they're interested in saying that they were doing everything independently of me, of my involvement. And I think they've gradually shifted more in the direction of cooperation. But it's not clear how things will progress. But I continue to be optimistic overall in the long run, but it's just in the short run, it's not clear how things will progress.
Yeah, thank you very much. A question about the availability, really, of data, the internet, large language models, etc., for students. How do we evaluate them now as mathematicians, as proof engineers, in this age where they have access to all these things? What do we need to do differently to assess them? And I guess if we all had the answers to that, we could spend the rest 5-10 years of our life traveling around and advising, set up a consultancy company.
Again, I'm not teaching maths, so although I'd like to teach some of the more maths-heavy courses, I'm employed to teach software engineering at the moment. But one of the things that we're leaning towards in that community is also people's ability just to explain things, which is obviously hard to scale, but that kind of whole notion of okay, can I actually concretely explain what's going on in something verbally quite often is increasingly becoming a consideration for how we can implement that at scale. But yeah, I would love to hear from people in the maths community as to what they're doing with this as well.
If either or other panelists want to come in on that.
Actually, just out of curiosity, I mean, how many courses now are taught in Lean? I hear words that there are professors now who are actually teaching undergraduate courses in Lean itself. Like intro to calculus is not starting by let f be a function, blah blah blah. The function is just like import mathlib. Like the entire course is actually. I hear that maybe in China there's some courses that are actually taught in this way, which that might be a very interesting way to go ahead. Do you guys know?
Paula had some data on it.
Yeah, there's that page, there's that page available where I think they encourage everyone who is teaching a Lean course, and Isabel has something, I'm pretty sure there's some resources similar, and other proof assistant communities. There's also something traditionally that was more software related than maths, which was the FMT group, I think, used to always keep a record of this kind of thing as well. So yeah, there's definitely a lot of people doing it. I think you still face a certain challenge there, if that makes sense. It's one thing, obviously, to integrate Lean into a course, but when you do then need to assess that foundational knowledge, that suddenly becomes more like the challenges that we're facing in software engineering, right? If especially say if one student can pay $20 or $100 and get access to this, and other students can't. You get this kind of interesting kind of phenomenon, even if Lean's in a course. Okay, well, how do we assess that? because taking it home and just kind of it suddenly becomes a little bit more tricky to manage. And so I think it's really exciting to see proof assistance being integrated into mathematical courses from early on. But I don't know if it solves the assess problem, if that makes sense. Yeah.
And I think
So-
go on, Shinichi.
Well, I'm sorry. So I just wanted to say that I don't currently teach undergraduates. I'm just teaching graduate students. But my problem is not that people a problem of how to assess people who use all sorts of tools like this. But my problem is how to get people interested in using these tools in the first place. Because the main problem that I have is that so I mean I can understand their feelings because I'm also and this is also my sense is that a priori I have an allergy to dealing with these kinds of AI and formalization, and so I'm sort of holding my nose while I do it because it's somewhat different from the traditional way of thinking of mathematicians. And the students that I typically get, with the exception of the certain type of student that comes from China, the typical students in Japan are also have this allergy, and they just don't want to deal with all these computer things, and they just want to think about mathematics in the usual way. And so my struggle is really to get these people interested in, and again I can understand their feelings because I was not originally interested in this kind of thing.
And I think the whole question strikes at the heart of what it means to be a mathematician or computer scientist or whatever it is that we're interested in, and how far being a research mathematician is from what we teach in the undergraduate curriculum and we expect our undergraduates to do, for example. And there is a sense, again, coming back to Yang-Hui's talk, where there is potential to close that gap in one sense, through that sort of mass exploration of data to bring students closer to what we can do, and with the use of large language models as proof assistants. But as we are renegotiating what it means to be mathematicians and researchers in an AI world, we are simultaneously having to think about what that means for our students and how to bring them into that world and yet still have assessments and outcomes that we believe in. It's a really difficult thing to grasp, and the humanities and social sciences are having it just as difficult, I think, if not worse. There's another question around, again, currently the use of AI seems to focus on the proving, but what are your thoughts on the ability of AI to actually help with the sort of engineering part, Chelsea, that you spoke a bit more about, and coming up with definitions that enable beautiful proofs, that sort of refactoring and enable reuse of results? So not just the calculation or can you get to that end result, but can we use large language models to help produce better definitions, better lemmas?
Yeah, so I know that this is something, so the second kind of project that a group from Sheffield, King's College, London, and Copenhagen are looking at in Isabel, one of the goals of that is to see if we can use AI for actually this kind of proof engineering element and creating more beautiful proofs and teaching. And so, yeah, I'm quite excited to see what that kind of group comes up with over the next few years. I know there's that exploration on the Isabel side, and to see what we might get out of it. Again, I still have this personal hesitation, and I'm willing to be proven wrong in several years as to what extent it can help with coming up with those definitions and settling on those definitions in the first place. I do think it's got a lot of potential in the refactoring, though, and so if we look at proof engineering in that kind of side of it, okay, we've done this one definition, we've formalized a heap of stuff in that. Actually, we think this better one, there's another one there that's going to be better. We don't really want to keep the old one. I think AI's got a lot of potential to potentially help with that aspect of the proof engineering process as well. But yeah, I think it's a good question, and there's a lot of unknowns in it at the moment.
Thank you. Just see if anyone else from the panel wants to jump in on that.
So I'm not an expert on proof engineering, so I don't have anything meaningful to say really. But I as someone who a priori is allergic to all of this, I would be very happy if AI could do it all for us, so that mathematicians don't have to do it manually. And so I look forward to having this develop further, but it seems very difficult. So I guess from a more abstract mathematical point of view, and close to a philosophical point of view, I thought that this discussion on the first day in Professor Paulson's talk about being able, can AI come up with a definition of a group? I think this is a very fundamental and interesting issue. And so, of course, one has to sort of, if one wants to do experiments like this, one has to sort of exclude the data that already exists in order to, so it's difficult to sort of create a substantial environment, I guess, where the AI can work with a substantial amount of data that, for instance, that is comparable to what some ancient civilization that did not have the notion of a group had. They would need, the AI would need this substantial amount of data. On the other hand, you want to deny the AI access to the data that we actually have, because that's already been contaminated with this notion. And so in other words, in order to develop this kind of AI capability further, one would first have to do experiments like this. So can you get an AI to come up with the notion of a group, just starting from a data set comparable to some ancient civilization, some generic ancient civilization. I would be very interested to see research on this, but I'm not an expert, so I can't really say anything.
Well, even in the classroom, I wonder how many of us really do this in terms of helping students to understand the role in creating good definitions in order to be able to prove the sorts of things one wants to prove, or whatever it might be. And I teach a third year course on graph theory, and we have at least 3 different definitions of graphs according to what we want to use it for. And of course, that's an interesting part of the conversation, and even getting the students to think about what they would want to define a graph to be in order to exploit certain properties. We have any more questions in the room or online, or any other thoughts from the panel?
Maybe just a quick comment. I think I'm not sure whether this is being done right now. There's a group that's taking archive from 1990 up to 1990 plus X training data, and then try to do 1990 plus X plus Y prediction. Maybe this is a very good thing to do for definitions, because I think they're just trying to generate. It's a bit vague what that group is doing in terms of trying to generate. This is something I always wanted to do for years, but I don't have the capacity to do it. But because of these companies, they can read now. Their large languages have become very good. But maybe this is a good thing to test. Definitions is a very important part of mathematical discovery. So can we train on all of the 1990 plus X data and just try to come up with things that are linguistically close to new definitions in the consequent years? Maybe that's a good experiment to do.
Absolutely. Learn lessons from statistics, right? You test the quality of a model by reforecasting, not by throwing all your data at it.
Yeah, exactly.
Lean for the curious math.
So there's an announcement in the room.
Oh, okay, no, maybe you need to. Yeah. Maybe I'll just see if I can share that as well. Yeah, hi, yeah, so I've just been asked to announce there's a meeting that Lean for the Curious Mathematician, so I'm just going to share that. And do feel free to, am I sharing that now? Yeah, I'll just share that now. All right. Yeah, so if anyone has any Isabel things they want to share as well, please do so. But I'll make it seem as though this is just a Lean thing. Yeah, so Lean for the Curious Mathematician is especially aimed at people who are interested in working on Lean, who are mathematicians but who don't have experience with interactive theorem provers before. Yeah, so I just wanted to share that, and I'll give it back to Barry for the panel discussion.
Well, I think if there are sort of no more questions either in the room or online, what we should do is we should thank the panel again and all the presenters from today.
Thank you very
It's
much.
been a real delight and pleasure to have you with us. Oh.
Yes, thank you.
Thank you very much. Oh, there is a question. What does the panel think that auto-formalization of all the literature, when does the panel think that auto-formalization of all of the literature will become a reality? And how will this change mathematics? So this is being a prophet, which Larry told us not to do.
Well, certainly not in my lifetime. I think I'm the oldest panel member. Certainly not in my lifetime.
Yeah, look, I'm dubious of completely, but also seeing just how quickly things have changed, I'm not going to make any predictions on that regard.
I think very wise.
I'm just going to quote Kevin Buzzard. I think I was with him at least virtually on Monday, and he says years and years and years. So I'll believe him on that.
Sure.
I wonder if he believes that it could possibly happen in his lifetime, if he seriously believes that it could possibly happen.
But the question was from him.
Yeah, the first question is from Kevin. So, I mean, Kevin is there. Maybe he wants to unmute and give him.
Let's ask Kevin.
Don't want to join?
Okay, well, let's leave it there. And oh no, Kevin has appeared.
Yeah. Oh wait. I was just there briefly.
Changed his mind.
Oh, finally! I finally figured out how to unmute. Sorry.
That's okay.
No,
We're
I don't know. I think it's an interesting question. I just don't know when it's going to happen.
Yeah.
So I wondered what the panel thought.
Sure.
Maybe within my lifetime. Sure. I mean, I talked to somebody earlier today who said 2 years.
And it's not an if question; it's a when question.
Sure.
That is true.
Yeah. No, well, again, difficult to predict, but I think it's going to be sooner than we might imagine. Certainly within the next decade, and probably sooner than that. It would be my guess, but that's a completely uninformed guess. Okay, well, we will leave it there, and thank you again for your contributions. And tomorrow the times change rather to accommodate other people on the other sides of the globe, etc. So please do check the new times, the times for tomorrow on the website, and we will hopefully see many of you tomorrow. Thank you again.
Thank you.
Thank you very much. This is a really fun conference.